Hello friends, welcome to part 3 of Classical Dynamics DSE paper 1 of 2023 Dibrugarh University BSc 5th sem, right? So we have already solved up to question number 3. In this video we're gonna start solving from question number 4a. And before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID, Ojha Lakhyajit, OJHLAKHYAJIT 123. Ojha Lakhyajit 123 is my Insta ID. You can follow me on Insta. So now let's start. So here is the question number 4. If a particle is slightly displaced from the point of equilibrium exhibiting small oscillations, then calculate the potential energy about a point of stable equilibrium. I have already solved this. Just go to the description box. There is a link where I have written 4a answer. Then I have provided the link. Click that link. You're gonna get the answer. Okay, where I have explained this. Now let's move on to next question. Question number 4b. Here, three rigid spheres are connected by light flexible rods with relative masses m1 is to m2 is to m3. Their ratios are 1 is to 2 is to 1. Right? Describe all normal modes of system and the normal frequencies. Here you see. Let me answer this question. Here you can see. Let me consider the mass of its sphere. So m1 is suppose small m, m2 be suppose 2m, and m3 is suppose m again, because here you see the ratios are m1, m2, m3. The ratios are 1 is to 2 is to 1. So we can consider that way. So suppose so let me make it small m1, small m2 and small m3 as mentioned in the question. Okay, so just wait, let me modify it. So small m1, small m2 and small m3. Okay, as in the question it is given that m1 is to m2 is to m3 is equal to 1 is to 2 is to 3. So we can consider m1 is equal to 1m, m2 is equal to twice m, and m3 is equal to thrice m. It's a very simple mathematical concept. Hope you know this. And assuming that let me clean these things. Okay, now assuming that the rod only allows translational motion along one direction. So these are the spheres, and here you see they are connected by with the help of rods, and as these rods you can see these rods are flexible. It is mentioned in the question. So we can consider these are this rod behaves like spring, right? And these allow only this spheres to vibrate in one direction only, right? That is translational motion. It allows translational motion, suppose along x-axis only. Let me consider that way. Okay, now here you see, let us assume x1, x2 and x3 denote the displacement of mass m1. Let's make here a small m1, a small m2 and a small m3 from their equilibrium position. Okay, so here this is first sphere, this is second sphere, this is third sphere of mass. This is m2 and this is m3. Okay, so they allow displacement from their mean position. You see, denote the displacements of masses m1, m2 and m3 from their mean position. It allows x1 displacement, and this displace x2 and this displace x3. Okay, from their mean position, like this way. Okay, so hope you have understood this. Since the rod is flexible, so as already I have mentioned that it behaves like a spring. So we have if it behaves like a spring, there must be a spring constant. Let it be k. Okay, let us consider it is k. Now here you see the equations of motions of m1, and that will be given by mx1 double dot, right? mx1 double dot. So these are the equations for m1. This is the equation let me take this as equation number 1, and let me take this as equation number 2 for m2, small m2. Let me write a small m2. Just wait, give me a second. This is small m1, small m2, and small m3, and this is equation number 3. Now you see, for the first one, this sphere, it oscillates this way, right? This is the initial position, suppose, right? And next to this is m1, next to it we have m2, right? When it displays x1 and it displays x2, then due to its displacement, its net displacement will be, x1 minus x2, and if we apply this formula, f is equal to minus kx, and this x will be replaced by x1 minus x2, and here f is mass into acceleration. Acceleration is x1 double dot, right? So hope you have understood this. So similarly, for this one, there is another sphere, that is m3. That's why here x2 minus x1 and x2 minus x3 occurs. Okay, so hope these things are clear to you, right? And similarly, for the last one, m3. For m3, last one, we have x2 on this side, m2 on this side, and on the other side there is no any other sphere. So again we have got the equation of motion of this form. And from these three equations, now you see, to find the normal mode of solutions, let us assume the solution to be this, right? And substituting this into the equations, these three equations, okay? And here for x1, amplitude will be a1, right? For x2, amplitude here will be a2. So similarly for a3 here, x3, it will be a3, right? So doing sure that what we will have, if you see, if you put this value here in equation number 1, suppose, let me show you that, then what you're going to have, x1, here you see, from this we're going to get x1 is equal to a1 e to the power I omega t, and x1 dot will be equal to a1 here you see I omega e to the power I omega t. That's what you're gonna have. And if you differentiate it again, then it's gonna be this I square, omega square, and this, then that's gonna be a1 omega square gives minus 1, right? I square gives minus 1, a1 omega square e to the power I omega t. Then this equation number 1 becomes m into minus a1 omega square e to the power I omega t is equal to minus k. Instead of x1 we're going to put a1 e to the power I omega t, minus instead of x2 we're going to put a2 e to the power I omega t. That's what we're going to put, right? So here from each and every term we can cut e to the power I omega, e to the power I omega, so on, right? So let me write it properly. Just wait, let me write it properly. Now you see, so from this first equation, what we're gonna have m instead of x1 double dot, we're gonna put this one minus a1 e to the power I omega t, right? Then on the other side, minus k. Instead of x1 we're gonna put this a1 e to the power I omega t, then minus x2. From this solution, x2 gonna be equal to a2 e to the power I omega t. That's what we're gonna have. So here a2 e to the power I omega t, that's what we're gonna have. Now you see, these things will be cancelled. So here it's supposed to be a2, okay, for x2, right? As we have x2 here, so this term is supposed to be cancelled, and after cancelling this, what we're gonna have, minus m a1, okay, minus m a1. Sorry, I missed this one. This omega square is missed out here. There should be a omega square here in this case. Just wait. So instead of x1 double dot, we should put minus a1 omega square e to the power I omega t, right? So here this e to the power I omega cancels. So here we have minus m a1 omega square is equal to, on the other side, k a1 minus a2. That's what we're going to get. So this is what we have got here, right? This is what we have got here from equation number 1, right? Similarly, from equation number 2 we're going to get this equation, and from equation number 3 we're going to get this equation, right? Hope you have understood this. So let me clean the things. Just wait. This is m1 and here is equation number 1. So pause the video and let me go to the next side. Here you see, divide each term by m. Here it was a2, okay, this is a3, okay, and here you see this is again a2, okay. So we have got this equation. What we have done here, we have divided both sides of these equations by m, and doing so we have got this. So it is k by m, okay, this is k by m. So hope you can recognize it. There is minus sign, okay. And let me represent this term by omega square, okay. Then this three equations, first, second and third, these three equations takes this form, okay, takes this form, and this is a system of linear equations a1, a2 and a3 that can be solved to determine the normal modes of corresponding frequencies. And solving these equations, we're gonna have a1, a2, a3 equal and omega equal to 0, okay. Symmetry. Here you see, when all the masses move together, okay. And next, here you see, first asymmetric mode, in the case when the middle mass is stationary and outer masses move opposite direction, then we're gonna get this a1 equal to a3, which is that's going to be minus a2 by 2, right? And omega will be equal to this, and so that's why we have got here mode 1, mode 2, mode 3, and here you see this is for the normal modes and frequencies. So here a2 is equal to 0 here, okay. So now what we have put here, it should be 2, a2 by 2, okay. So that's all what we needed to do in this problem. So let's take the next question. Now we're going to solve question number 4b, or question number 4b, or this one. So that the total energy of coupled system with 3 degrees of freedom, that means again we're going to consider 3 masses, m1 and m2, m1, m2 and m3. So now let me tell you one more thing. Coupled means they are joined, okay. It doesn't mean that there are 2 masses. Here we have 3 degrees of freedom, so we're going to consider 3 masses here, okay. Let me clear that things, okay. So here we need to show that the total energy is sum of the energies of each principal mode of oscillations. So let me give you the answer. Question number 4b, or starts from here. 4b, or okay, starts from here. Let us assume that we have 3 masses, m1, m2 and m3. It's connected by springs with spring constant k12, k23, etc. That means let me show you this one. This is m1, this is m2, this is m3, connected by the springs k12 and k23. The spring connecting m2 and 3 is k23, and spring connecting m1 and m2, its spring constant is k12. Let me consider that way, okay. And displacement of these 3 masses from their mean position is taken as x1 and x2 and x3. That's how we have taken, right? And here again for this couple system, this is xi, which is function of t, right? So generally satisfy this matrix form, right, of equations. Okay, satisfies a set of couple differential equations which can be written in the matrix form. This is the matrix form where k is equal to this, x is equal to this matrix. Okay, and m is the mass matrix, and k is the stiffness, a spring constant, you can say, a matrix of spring constant. Okay, so now let's move on to the next page. Here you see, to solve these equations we look to normal modes by assuming the solution to this, as we have already done in the previous slide, and substitute this solution in the matrix that we have taken here. Okay, then you're gonna get this. Then total energy is given by kinetic energy plus T means kinetic energy, V means potential energy, kinetic energy plus potential energy, and kinetic energy is this, and this is the expression for kinetic energy. T is equal to half summation from 1 to 3, that is MICI dot square, right? Here summation takes place from I is equal to 1 to 3, right? Hope you can see it. Now let's move on to next page. Here you see the potential energy is given by this expression, and here is the potential energy. So instead of writing this summation this way, let me write this way: summation from I is equal to 1 to 3. Okay, from I is equal to 1 to 3. So this is the expression for potential energy. Let's put here, this is the total energy expression, and so this is the total energy expression, which proves that you see this is the last thing that we needed to prove. That is what? Let me go back to the question. So here you see what we needed to prove. We need to prove that total energy is the sum of energies of its principal mode of oscillation. So here it is proved that total energy is the sum of its principal mode of oscillations, right? So hope you have understood this. So this is represented by this here summation. This is for particular height, okay, and total energy is this summation from I is equal to 1 to 3, and if you put I is equal to 1, 2 and 3, here you're gonna get 3 terms such kind, okay, and their sum is the total energy, right? So that is what we needed to prove. Okay, now let's move on to the next question, and this is question number 5a. State the postulates of special theory of relativity. So let me show you the postulates. So this is the 5a answer. The two fundamental postulates of special theory of relativity. This is 1, this is 2. Just pause the video and note it. Right, now let's move on to next question. Now 5b, here we need to write short notes. Length contraction, I will provide a link in the description box. 5b answer 1, okay, then link will be there in the description box. Then because I have already made a video on length contraction. Then now let me give you the answer to this. So let me show you twin paradox. So you can write this 5b2 answer, twin paradox. So just pause the video and note it. And now last one, and question number 5b3, momentum for vector. Let me show you this one also, and I will solve this numerical in the next video. Okay, here is the momentum for vector. Just pause the video and take the note, right? So thank you for watching. See you in the next video.